Hello, more statistics today. Exercise 7G, exponential distribution. So one thing we've seen before is something linked to this, and it's called the Poisson distribution. And the exponential distribution is linked to that. So I'm going to start off with an example. It says the number of organic particles in 100 milliliters of pond water follows a Poisson distribution with mean 20. So you should remember that you'd write that as x is Poisson 20. Find the probability a volume of 10 milliliters contains 3 particles. So straight away I'm having to change my x because I haven't got 100 mil. I've got 100 mil is mean 20. I've only got 10 mil in this, so presumably it's Poisson. It's a tenth as big, so it's Poisson 2. I'd expect to get 2. That's basically what it's saying. And it's saying what's the probability that I actually get 3. And I can just do that on my calculator, so I'm not going to faff around with the equation. I'm going to go stat distribution rather, and I shall go to the Poisson PDF. Lambda is 2. My x value is 3. And what's my... I get 0.18. So just using the calculator button, you could use a formula if you prefer. 180 to 3 significant figures. The value of x, so this is a backward one, as you can tell straight away. There are more than x particles in a volume. Is a volume of 80. So again, I need to adjust my Poisson distribution. For 10 it is 2, so for 80 I think I've got 16. I expect to get 16, but there's a 0.2577 chance for the whatever I get, and it's that I get more than some number. So just think about this. What I'm expecting to get 16. So if I got more than this number, there is a number up here which I'm trying to find. I shall call it x. And the probability of this happening, it says, is 0.2577. So by definition, the thing about these calculators, of course, they always give you less thans. So the probability that x is less than or some number, capital X, is equal to 1 minus 0.2577, which is 0.74. 2, 3. Hopefully I've got that right. That's a 3 here. Just check that 1 minus 0.2577. A bit rusty on there. 7423. Good. So I'm just looking for that answer. You know, you could use a Poisson method of doing it. I'm just going a bit of trial and error. I'm expecting to get 16. So it's got to be bigger than 16. So let's try again. Distribution, and go up to the Poisson CDF button. And 16 is my lambda. Pick an x value. Let's pick 20, and let's see what that says. That says 0.868. And I'm going to keep trying with this until I get my answer. Hopefully you could do the same. Right, I just tried 18. That gave me the one I wanted. Where's it gone? So the probability that x is less than or equal to 18, I think, is equal to this. So when it's 18 or less, I get that, and that is the equivalent. So let's see if it's 18, and 18 is the answer. So, and the first one was 0.180 as well. So the geometric distribution then is where you look at the binomial distribution. You keep doing it until eventually you get success. So the idea of the exponential distribution is meant to be analogous to it. It's meant to be the case that you keep weighting. Likewise, the exponential distribution, it says, models the weighting interval until an event occurs in the Poisson distribution. So if you take that example, how long will it be until I get a certain event occurring? How much water will I need? I suppose how long, if I'm searching for something, how long would I have to walk before it happens, and so on. So this is the formula that we are given. F of x is lambda e to the minus lambda x, and rather kindly they say it will tell us in the exam. And we've got two things here, the expectation and the variance, and they should look fairly familiar from the Poisson. Using integration, then we can also find it says a CDF, a cumulative distribution function, and obviously you now know that that's written with a capital F of x, and it's naught for any number of x less than 0, but then this is the formula. So effectively this is the formula we can use. So and I've written down there that effectively this means that the probability that x is less than some number x is equal to this. That's what the CDF is, isn't it, up to that point? But if I want more than, I have to do 1 minus e to the minus lambda x, which is just e to the minus lambda x. So let's bear that in mind as we go through a couple of questions. Now, first of all, this is meant to say example. It's actually a proof, and it says prove that e of x is 1 over lambda x. And of course, we saw when we did the uniform distribution, the way you do these proofs is you go back to basics. We know that e of x for any function is the integral from x f of x dx between two values a and b. And we just saw that e of x is f of x is lambda e to the minus lambda x. So I can write x lambda e to the minus lambda x, and I have to integrate that between a and b. And obviously this is something where I can take the lambda out, but it doesn't really help me much because I've still got x e to the minus lambda x dx, and this looks to me to be integration by parts. So I'm going to set my, well, first of all, I suppose I should go through the process. Late rule, I've got an algebraic term, which is the x, and I've got an exponential term. So you can see my algebraic term is the higher one up. So my u is going to be my x, and my dv by dx is going to be my e to the minus lambda x. My du by dx therefore is equal to 1, and my v equals, you may recall how to do this, it's minus 1 over lambda e to the minus lambda x. So I chuck this into my equation, I get lambda times by, now remember the formula is uv minus the integral of v du by dx dx. So lambda times by u times by v. So that's x times by, well, minus 1 over lambda e to the minus lambda x minus the integral of that same thing. Again, it's a minus, so I can just ignore it. And notice, by the way, that's times by 1 when I do that. So 1 over lambda e to the minus lambda x. And that's why we can do that, because effectively this now is integratable. So it's, well, the great thing about this actually is you can just see that's lambda times that, so, and lambda times this, and they're both on the bottom, so it cancels that. So I think a lot of those lambdas disappear. This becomes minus x e to the minus lambda x plus the integral. Now this, when I integrate this, then the minus lambda comes down on the bottom again, so I think I get minus 1 over lambda e to the minus lambda x. Between a and b, remember this. So I can chuck b in. I get minus b e to the minus lambda b minus 1 over lambda e to the minus lambda b. Put the a in, minus a e to the minus lambda a minus 1 over lambda e to the minus lambda a. Now this looks pretty horrific until you just think about this for a moment. As much the a and the b aren't quite the same in this case. You can't, for instance, on this question, go any lower than 0 for if you're waiting for a time period or whatever. So the a effectively is 0, and the b could go up to anything. So this could go up to infinity. So even though it looks horrific, I think it will actually sort itself out quite quickly. The b then is a big number, but e to the negative infinity, which this is 0. So that disappears. So 0 minus 1 over lambda. Again, this is 0. Are they all zeros? Oh, right, no, they're not. These are zeros. I was just thinking to myself that I think this is 0. When I put infinity in there, I get 0. But if I put 0 in there, that's the difference. So it's minus. Now, e to the 0, that gives me 0, effectively is 1. So this gives me a minus a times by 1, so I can ignore that. I can ignore that. Well, what was a? A was 0. So that's got a 0 as well. This one hasn't got a 0. So this is minus 1 over lambda times 1. So after all that, 0, 0, minus times that, but minus times a minus is a plus. I eventually get the answer, 1 over lambda, which was the answer. Well, that's a bit of a mess, until, of course, you start thinking about zeros and infinities rather than a's and b's. So I've got an example here. A sewer pipe has an average of 3 leaks every 2 miles. I suppose that really means it's got 1.5 leaks per mile. An inspector enters the pipe at a manhole and then walks along it looking for leaks. Find the probability of the first leak. Now, this is an example then where it's exponential, rather than just Poisson. Poisson would basically say if I had if I walked for 10 miles, how many leaks would I find? This is, what's the probability that I will find my first leak in the first half mile? So this is exponential. Well, I remembered how to write that properly. It should be a capital E. Other than that, that's right. An exponential 1.5. And we had formulas for this, if you remember. So we're going to have to do the probability that we basically get an x value. We get our first one within the first half mile. I suppose that's between 0 and 0.5. And I'm going to integrate this from 0 to 0.5 then. And it's going to say 1.5 e to the minus. Lambda was 1.5 as well, to the x. And if you're wondering where this comes from, let's go back. This is this formula here. So I've found my f of x. And I want to find the probability, and you should remember that all probabilities you integrate f of x dx. So that's all I've done really. So I'm integrating that formula I gave you. So if I integrate this, what do I get? I get, well, I just have to divide by that 1.5. So I actually end up with getting 1.5 over the minus 1.5. E to the minus 1.5 x again, between these two values. And you'll notice this 1.5 over 1.5 will always cancel out. So we can save ourselves a bit of time. It's minus e to the minus 1.5. Now I've got to put in 0.5 and then I've got to put in 0. Because really these are the intervals that I'm playing around with. So if I put times by 0.5, of course when I sub in the 0, I will just get minus e to the 0. So I'll just try and squeeze it in here. That effectively, let's just do that sum. Just type it into my calculator. And I get 0.528-ish. Now, you'll notice a few things there. When you're doing that, this will always be 1. Effectively, this was the other formula we had. So I'll just go back to that. Now, I did say if you do some integration, which we did, the probability will always be 1 minus e to the minus lambda x. So it might be worth just remembering these formulas instead, and just saying to yourself, well, if I remember those, then I don't have to do any integration. I just jump straight to it, because that's effectively what we just ended up with when we did this. This was the 1, and this was the minus e to the minus lambda x. So that might be easy to do that. The variance, again, we had a separate formula for the variance. It was, I think, let's go back, it was there, 1 over lambda squared. So 1 over lambda squared. Well, that seems quite easy to me, that it's 1 over 1.5 squared. Now 1.5 is 3 over 2, square root is 9 over 4, that should be 4/9 then, according to me. And it was 4/9. So in lesson we'll do exercise 7G. I've got at least one more example to show you, so hopefully it all makes sense then. Best of luck.